Hello everyone. Hey guys, this is me Megha, your JEE educator, and today in this session I'm going to discuss with you some of the important terms for the chapter periodicity in properties. So if we want to learn the periodic trends, then these are the three topics, the most important topics that we all must need to know about them. The shielding effect, the effective nuclear charge, and the Lanthanoid contraction. So let us go in detail that what they are all about. Shielding effect. Shielding is also known as screening. Is screening. So what do you mean by the shielding? If you would ask me, then I would say, Pacha, shielding means protecting. Okay. So what protects? So protects just like when in the cozy winter days, your blanket act as a protection, right? So the blanket protects you from the heavy winters. So just like that, here we will be having this as a blanket. These are basically the inner shell electrons. These are the inner shell electrons, and what these inner shell electrons will do? These inner shell electrons will try to protect the electron, will try to protect this electron. So our aim is to protect this particular electron. We want to keep this electron safer. So here these are the inner shell electrons which will act as a protection for this particular electron. So basically what is going to happen, this nucleus is very powerful and this is a positively charged nucleus. This nucleus wants to attract this electron towards itself, and if this nucleus will be able to attract this electron towards itself, then the size of the shell decreases, then the size of the atom decreases. Okay, so basically we need to know that what is their shielding effect, what is their protection, that what kind of protection um, they could be providing. Okay, so this is the shielding or the screening effect, the shielding or the screening effect which can be shown by the inner shell electrons. So basically guys, this is a property of a multi electron system. So whenever you have a multi electron system, when you have a more than one number of electron system, then only the shielding effect can be applied. And the shielding effect is a property of the shapes of the orbital. This means that the shielding effect can be determined by the shape of the orbital, whether the shape of the orbital is S, P, D or F orbital. So the shapes of the orbitals determine the shielding effect. So basically what happens? So this is basically the decrease in force of attraction by nucleus. So this nucleus wants to attract this particular electron towards itself. So the decrease in force of attraction by nucleus due to the repulsion by inner shell electrons. So what will happen? These inner shell electrons will keep repelling among themselves. As you can see that they are the like charges. So these electrons will keep on repelling with each other, and because of the reason that they will keep repelling with each other, what they will do, they will try, because of this repulsion, they will protect, they will shield the last shell electron from the effect of the nucleus. And when there will be a decrease in force of attraction by nucleus due to the repulsion by inner shell electron, then this is known as the shielding effect. This has been found that the shielding effect by the s orbital is much greater than the p orbital, than the d orbital, than the f orbital. Because as I told you that this is the property of the shape of the orbitals. So this has been found that the s orbital shields more strongly as compared to that of the p, then d and then f orbital. So what's the reason behind it? So let me try to explain this concept to you guys. In the s orbital, we know that in the s orbital we have maximum of 2 electrons. So yes, the 2 electrons will be distributed. Okay, so we all know that that the shape of the s orbital is spherical, the p orbital is jumbled shape, the d orbital is double shape, and the f orbital is having a complex structure. Okay, so we all know the shape of these orbitals. Okay, so what I want to tell you is I am just talking about the size of orbitals. Okay, so I am not talking about the shape right now. These are the shapes of orbitals, but right now I want to talk about the size of orbitals. So this, I just want to replicate that the size of s orbital is very small, then the p orbital is bit larger, the d orbital is big more larger, and the f orbital is very big. So here we know that in the s orbital we do have 2 electrons. In the p orbital we do have 1 to 6 electrons. We do have maximum of 6 number of electrons, 1 2 3 4 5 and 6. In the d orbital we do have 10 electrons, 1 2 3 4 5 6 7 8 9 and 10. We do have 10 electrons. And in the f orbital we do have 14 electrons. In the D we have 1 to 10, in the F we have 1 to 14. This means that we will be having 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So what does this mean? This means that, guys, the size of the f orbital is so large. The size of the f orbital is so large that though it has 14 f electrons, but these electrons are strongly away from each other. These electrons are very away from each other as compared to these electrons and these electrons. Can you see this thing? So which electrons are very much away from each other? These electrons which are in the f orbital are much away from each other. They are that much away from each other that they don't undergo even repulsion. Okay, so they have a maximum repulsion. And here this has been considered that these electrons are so away from each other, they are so far away from each other that they don't even repel. They are already so much away from each other that the force of repulsion even don't works over there. Okay, so what I want to convey is, guys, I want to tell you about the electron density. So if we can understand that the size of the orbital is increasing, the size of s orbital is very small, then the p, then d and then f orbital is very big. So as the size increases, the electron density decreases. Though you know what is density? Density is equals to mass upon volume. Okay, so then what do you mean by this? You know that you would say, ma'am, in the f orbital there are 14 number of electrons. Yeah, that's true. In the f orbital there are 14 number of electrons. The mass is so high. But guys, relative to that mass, this volume is also very high. Okay, because here the mass is increasing, but with respect to mass, the size is increasing much larger. Okay, and so because of that particular reason here, because if this denominator portion will increase a lot, then the density decreases. And if the density decreases, when the electrons are very away from each other, that they don't even repel. So let's consider if these electrons are so away from each other that they don't even repel. Okay, let me tell you here only. So if these electrons are so away from each other that they don't even repel, then what will happen? Even if we will be having the last shell electron here, and these electrons are so much away from each other that they are not even repelling, then the shielding effect caused by this particular orbital decreases. Then what I am saying, that the shielding, the protection that these electrons could provide, the shielding effect decreases. So are you getting why the shielding effect decreases? Because if the electron density decreases, the electrons are so much away from each other that they are not even repelling, then this portion becomes free. So this all portion is becoming free. So there is no one to protect, there is no one to shield or no one to screen. So if there is no one to screen, then the nucleus is much powerful, and this will try to attract this electron more strongly towards itself. And so therefore the shielding effect decreases, the electron will get attracted towards the nucleus. The electron get attracted towards the nucleus. Conclusion. So this will be the conclusion, okay, that what will happen. So I hope you understood that what is the shielding effect. So again, let me repeat, shielding effect is basically the property of the inner shell electrons. Shielding effect can only be determined in the multi-electron system. So we always talk about the last one electron. Okay, so the last one electron will be shielded by the other all electrons. Okay, so just like when there is a cricket match, one of the player is like doing a batting, so the others are doing the fielding, no? So similarly the same way, so if one of the electron is there and we are evaluating the effective nuclear charge over that particular electron, then what these inertial electrons are doing? So these inertial electrons are basically, because of their because of the repulsion in between the inertial electrons, because of the repulsion in between the inertial electrons, when they repel so much, or when they goes that much away from each other that there will be no repulsion, they go so away from each other, the shielding decreases, and as the shielding decreases, the electron will get attracted towards the nucleus. Okay, so this is it, this is what I want to tell you. So as the electron density decreases, the shielding effect decreases, the shielding effect decreases. Okay, so now here comes the another topic, that is the effective nuclear charge. And the effective nuclear charge can also be said to be Z effective. So now what do you mean by that? So guys, as of now, these two things are interrelated. So as of now, I told you that as the shielding by these inertial electrons decreases, as the electron density decreases, as the size of the orbital increase, the electrons gets more distributed, they will be very away from each other. As we know that the f orbital is very much diffuse means it's spreaded, it is having a large size, so it is spreaded. So here the electron density is less, so as the electron density is less, they will not be able to shield, they will not be able to shield what? They will not be able to shield the last electron from the effect of the nucleus. And when they will not be able to shield the last electron from the effect of the nucleus, this electron get attracted by the nucleus. So ultimately what is happening? So because of the poor shielding, because of poor shielding, the nucleus is becoming more powerful. We can say that the effective nuclear charge is increasing. The effective nuclear, because of the poor shielding, the effective nuclear charge is increasing. Okay, so this is what we could say. So here we can say that Z effective is equals to Z minus sigma. That is the effective nuclear charge. The effective nuclear charge, this is the effective nuclear charge. Okay, yeah. Effective nuclear charge is equals to Z. Z means the atomic number. So atomic number basically tells you about the number of protons. So as much as number of protons you will be having, that will be the charge of nucleus. That will be the charge of nucleus. Okay, so that's how this is the charge of a nucleus, that is the Z minus sigma. Now what is a sigma? Sigma is the shielding effect. So as I said, as the shielding effect and the sigma, the shielding effect can also be calculated by the Slater's rule. Okay, and which is also known as the shielding constant. So yeah, we can calculate this value, that which orbital is doing how much of shielding, s orbital, the number of the number of electrons which are present in the s orbital, how much strongly they are shielding the last electron, or the electrons which are present in the d orbital, what is their shielding effect. So we can calculate it, and this can be calculated by the Slater's rule. So what I want to say is, if what will happen, so if we have to minus this sigma, we have to minus this repulsion. Why? Because as you know that this z is for the nucleus charge, nuclear charge. So what is this nuclear charge? Nuclear charge will basically try to attract. So as the nuclear charge increases, the attraction increases, and sigma, the sigma is what? Sigma is basically the shielding by the inertial electrons, that is the repulsion by the inertial electrons. The shielding is basically the electron repulsion by inertial electrons. So if I say ki as the sigma, that is the shielding, as the shielding increases, so if this value increases, if this shielding increases, what happen? If this shielding increases, sigma increases means z minus sigma value decreases, means z effective decreases. So if in case the shielding increases, the z effective decreases, means the effective nuclear charge caused by the nucleus decreases. means the nucleus will not be able to attract the last electron more firmly because its Z effective decreases. And if you say that here the repulsion decreases, that is we can say no, we can say ki here if so we can say that Z effective and sigma are inversely proportional to each other. If the shielding increases, if the shielding, the protection by the inner shell electron increases, then what will happen? The nucleus know how the nucleus will be able to attract the last electron towards itself. This means that the Z effective decreases. I hope this point is very clear to all of you. So we can say that as the sigma increases, the Z effective decreases. They are inversely proportional to each other. So shielding effect and the effective nuclear charge is having a relationship between them. Okay. So guys, here we came to a conclusion, that is Z effective. Z effective when we are moving from left to right, as the atomic number increases, as the Z value increases, the atomic number increases, the number of protons increases, the Z effective increases, the Z effective increases. But here we found that when we are moving from top to bottom, the Z effective remains constant. That means that there will be no change in the Z effective values when we will be moving from top to bottom, because this is a property of the shape of the orbital. Okay, so when you are moving from left to right, yes, you are having the 2s1 configuration, then you are having the 2s2 configuration, then you are having the 2s2 2p1 configuration, means the number of electrons which are getting filled in a particular orbital are getting changed, and so therefore the shielding effect is getting changed and the Z effective is increasing. Okay, so here you will be having 2s2 2p2, 2s2 2p3, but here what will happen? This is 2s1, this is 3s1, this is 4s1, this is 5s1. So the shape of the orbital, in the shape of the orbital, is there any change? No, there is no change. So what I told you, that the shielding effect is the property of the shape of the orbital. So if in the shape of the orbital there is no change, this is S1, 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 so there will be no, so the shielding effect will remains the same, and if the shielding effect will remains the same, they will the Z effective will remains the same. Okay, so there will be no change in the Z effective values because the orbital remains the same. The number of electrons present in the orbital remains the same. Got my point? Okay, so when you are moving from top to bottom, the Z effective almost remains constant. Now there is one more thing that I would like to tell you, that is the lanthanoid contraction. We have found that in the lanthanoid series, that is if we go from LA to LU, LA is basically 57 to 71, that is our lanthanoid series. If we go, there is a gradual decrease in size. We can see that the size decreases. LA is bigger in size, then the CE, the size decreases. So why there is a decrease in size? Okay, so basically guys, in the lanthanoid series, I want to mention the Z effective values is same for all. Why I am saying yes, this is an important point to mark. That is, in the case of the lanthanoid series, the Z effective values are same for all. Because in the lanthanoid series, if you have to fill the electronic configuration, then what it would be? This would be the 6s2 electron, 4f1 to 14, 5d 0 to 1 and 6p0. This means that you are filling the last shell electron into the f orbital, which is 1 to 14. And you know, F orbital is so much diffused. F orbital is so large in size. This is F orbital is very much diffused. F orbital is very much diffused. Very much diffused. That is the that is when the electrons enters in the f orbital, when the electrons enters, when I have to enter these 1 to 14 electrons in the f orbital, they will be go like this, as the size of the f orbital is so large, so they don't even repel. There will be no electron repulsion. So when the electrons are entering in the f subshell, which is very much diffused, there will be no electron repulsion. So if there will be no electron repulsion, then will there be any shielding? No. Then there will be no shielding. and when there will be no shielding, they will be having a poor shielding effect. So there will be no repulsion, means there will be no shielding. If there will be no shielding, then the Z effective, then there will be no repulsion, means no shielding is there. So F orbital, in the F orbital there is no shielding. So ultimately the Z effective remains the same for all. So but what is happening? Then why the size is decreasing? If the Z effective is same for all, then why the size is decreasing? Guys, the size is decreasing because of the fact that as we move from left to right, the atomic number increases. So atomic number means if the atomic number increases, means the nuclear charge increases. If the atomic number increases, means the value of Z increases, means the nuclear charge, the charge caused by the nucleus increases, and hence therefore if the charge by the nucleus increases, the attraction for the electron increases, and since the size contracts, and as the size contracts, this contraction is known as the Lanthanoid contraction. Okay, so this is the Lanthanoid contraction, the decrease in the size of the F block elements. The gradual decrease in the size of the F block elements is basically known as the Lanthanoid contraction. So Lanthanoid contraction is not because of the reason that the Z effective increases. No, here the Z effective remains the same for all. Why the Z effective remains the same for all? Reason being, the electrons are entering into the F orbital, which is so large in size, the electron density is so small, the electron density is very low, so there will be no repulsion, and if there will be no repulsion, there will be no shielding, and hence the Z effective will not work there. Okay, the Z effective will remains the same. Now here when I discuss with you the Lanthanoid contraction, you would be surprised to see, then ma'am, what are these? Why you have made those humps? Okay, so basically the size of EU and the size of YB is bit larger as compared to the size of the other elements. The reason being, they all are metals. Okay, they all are lanthanoid elements and they are all metals. Okay, they all are metals, though they are less metallic than the S block elements, but they are metals. And if you would see in the metals, there will be the metallic radii which will decide their size. Okay, so here when you will be talking about all the Lanthanoid elements, there we will be having M plus 3 electron, the most common oxidation state. The most common oxidation state is found to be plus 3, and so therefore 3 electrons participates in the bond formation, in the metallic bond formation. But when you will look for the YB and EU, in the case of the YB and EU, the YB, the configuration is 4f14 6s2, so this just wants to lose 2 more electron to attain the 14 to attain the full filled configuration, and the fully filled configuration is much more stable. And similarly in the case of EU, if you will be losing 2 electrons, then the configuration will become 4f7, which is the half filled configuration, and the half filled configuration is much more stable. So here in the case of YB and EU, because of the half filled configuration, because of the half filled and fully filled stable configuration and fully filled stable configurations, they are just contributing 2 electrons. And so because of this reason, there the size increases. Okay, because only 2 electrons are participating for the metallic bond formation, but here the 3 electrons are participating in the metallic bond formation. Or in the another way, you can also understand it like this: if any of the species will be in its plus 3 oxidation state, plus 3 means more the positive charge increases, the size decreases. So if you will be talking about M plus 3 and M plus 2, so M plus 3 the size will be smaller rather than the M plus 2. Okay, so as there will be the loss of more number of electrons, the Z effective increases and the size decreases. Okay, and so therefore YB and EU are larger in size. Now there is one more thing. So what is the application of this Lanthanoid contraction? Do we need to know? Yes, absolutely. If you would take the case of thallium, in the case of thallium, we can see that there is a Lanthanoid contraction. Why there is a Lanthanoid contraction? Because if you are talking about the thallium, we have 6s2, 4f14, 5d10 and 6p1. So we have 4f14, 5d10, 6s2 and 6p1. Okay, so here we will be having one electron which we will be talking about. Okay, what would be the size of the thallium? Okay, the size of the thallium will be determined by the nucleus. So this nucleus will try to attract this particular electron towards itself. Okay, but what these inner shell electrons will do? These inner shell electrons will try to do the electron repulsion. Okay, so when they will try to do the electron repulsion, they will act as a shielding. They have to do the shielding. They have to shield the last electron from the effect of nucleus, so now we want to see whether they will be doing a good shielding or they will be poorly shielding. So guys, here we know that there we have the 4f14 electrons. So here we have the 4f14 electrons, and the f orbital is so large in size. And if the size of the f orbital is so large and the electrons are so much away from each other, they will not be doing the proper shielding. And if they will not be doing the proper shielding, the electrons are so much away from each other, this nucleus becomes more powerful, and this will try to attract this electron more tightly towards itself. And so because of the reason, the poor shielding by the lanthanoid series, that is by the 14f electrons, what will happen? As the shielding decreases, as we know that here the Z effective, what will happen to the Z effective? As we know that the shielding, because of the f orbital, the shielding decreases. So if the shielding decreases, means Z minus sigma value increases. If the sigma value is very small, then Z minus sigma value becomes bigger. So means the Z effective increases. So ultimately the Z effective increases, and if the Z effective increases, this nucleus will try to attract this electron more firmly towards itself. Okay, so as the effective nuclear charge increases, the nucleus held the last shell electron more tightly, and so therefore the size decreases. This decrease in size is due to the lanthanoid contraction. Okay, so this is the application of lanthanoid contraction. Okay, so this is the application of lanthanoid contraction. But if you would look into the lanthanoid series, there is no change in Z effective. Okay, so this is what I want to tell you guys. This is all about the shielding effect, the Z effective, and the lanthanoid contraction. So here we do have so many applications of all these three terms while determining the atomic size. When you will go through left to right in the period, you will find that the size decreases. Why the size decreases? Because the Z effective increases. Why the Z effective increases? Of course, as the nuclear charge increases, as I told you, Z effective is equals to Z minus sigma. Okay, so here the sigma value is very low, no? So here if you will be going from left to right, here the sigma value is very low. So when the sigma is very low, the shielding, because here we do have only s and p orbitals. Okay, so the s and p orbital so here what is happening? The number of protons are increasing. And we know when the sigma, that is the shielding, they are doing if the shielding decreases, the Z effective increases. Okay, and if the Z effective increases, the size decreases. Okay, so this is it. So this is the application of Z effective. Then the application of lanthanoid contraction can be seen in the case of the thallium. I have already taken this as an example. And the scandite contraction, similarly, because of the poor shielding of the 10d electrons, because the 10d electrons, of course, we have seen that as compared to that of the size of the s and p orbital, d orbital is also a bit larger, and this also has the maximum electron repulsion. So because of the maximum electron repulsion, there will be poor shielding, and when there will be a poor shielding, this means the sigma decreases, the Z effective increases. Okay, always remember sigma and Z effective are inversely proportional to each other, and if the Z effective increases, the size of the gallium decreases. That is the scandite contraction. Okay, and similarly this is for the actinoid contraction as well. So thank you so much guys. I hope you understood all the three topics very firmly. So please like, share and subscribe for this particular session, and if you are enjoying learning through me, then please do follow me on Unacademy. Here is my profile, and don't forget to follow me there. So here you please click on the follow button, and the link is given in the description below. Thank you. Have a nice day.